Okay, Assalamualaikum warahmatullahi wabarakatuh, and good evening to all audience. Okay, welcome to our webinar series, Faculty of Engineering and Built Environment, Masa University. Okay, my name is Muhammad Sabiri Mirahmat. I'm moderator for this webinar today. Alright, alright. Before we start our webinar, let me introduce our uh, webinar speaker. Okay, our speaker is Professor IR Dr. Abdul Aziz bin Abdul Samad. He has he has experience in academia for 30 years. Okay, he gains his bachelor degree in civil engineering from University of Glasgow, United Kingdom. Then he obtained a master degree in structural engineering from University Strathclyde, United Kingdom, and is awarded a PhD from University of Manchester, United Kingdom. Now uh, he also joined University Putra Malaysia, okay, as associate professor in 1988 uh, and by 1998. Okay. After that, he joined University Tun Usain on Malaysia, okay, UTHM, as a professor in structural engineering until his retirement in October 2020. Okay. Uh, Among his research, uh, his interests include industrialized building system, sustainability of reinforced concrete structure, and green concrete. Being a qualified engineer, he became a corporate member of the Institute of Engineer Malaysia in 1998 and was a registered professional engineer with Board of Engineers Malaysia since 2011. Okay, by 2019, he successfully upgraded his professional registration with the Board of Engineer Malaysia as professional engineer with practicing certificate (PEPC). In November 2021, the Academy of Professor Malaysia acknowledged his contribution to science, engineering, and technology and has therefore conferred him as Fellow uh, or FAPM. He then joined Masa University as a professor with the Faculty of Engineering and Built Environment since 10 January 2022 until this present. So this is a little bit the background of our webinar speaker today. So I would like to invite our webinar speaker to deliver their speech. Now, Prof. IR Abdul Aziz, the platform is yours.
Okay, thank you very much, Dr. Sabirin, for your very kind introduction about me. Very humble to be here in front of all of you, my fellow colleagues from the faculty, my fellow colleagues from the university, and also and for those who are interested in listening to my webinar talk this morning. I welcome all of you, and I wish all of you uh, safety among our friends. Yeah. So my talk today will be on the title, as you can see on the screen, is an innovative green concrete mix integrating 4 different types of waste materials. Now, this title is related to my research work that I conducted, myself and my students conducted a few years ago. This is under the Fundamental Research Grant Scheme, Fundamental Research Grant Scheme, FRGS, vote number 1573, awarded by the Ministry of Higher Education. My thanks to the Ministry for awarding this grant. And the grant is entitled Strength Prediction of Green Concrete Interlocking Block from palm oil fuel ash, palm oil fibre, rice-husk ash, and recycled aggregate waste material. Now, before I go deeper into my research results and discussion, just let me bring to you about the current event that we have now. Of course, as we know, we are now facing a situation where our climates are changing due to various reasons, as I'm sure you are well aware of, whereby we have now, in Malaysia itself, we have now various heat waves, we have floodings, we have extreme rain, and sometimes we also have droughts, but I don't think we have severe droughts yet. But we do have the first three, as I mentioned, heat waves, flooding, and also heavy rain. And once in a while, we may have also small tornadoes from here, from time to time, as we can see, from various social media, that we can see some little tornadoes spinning here and spinning there. But we do have all this situation in our country, and we must be aware of the situation. So all this is because of due to the climate change that we are facing, not only in Malaysia, but also all over the world. Now, recently, as you can see from this slide, this is a slide taken from the Malay Mail, okay, dated 29 December 2021, just last year. And this is the flooding situation at Taman Seri Muda Shah Alam, Selangor. So as you can see, it's quite a bad situation. And of course, this is not the first time that this particular area has faced flooding. And I believe, and I've read somewhere, that this was the fourth time for this year alone that Taman Seri Muda has faced flooding. So this is a very unfortunate situation for those occupants at this Taman Seri Muda. So, and again, the situation arises because of the heavy downpour, and well, other than issues like drainage issues and all that. So, but besides that, this is also because of the heavy downpour that has been facing our country about that time. And we also hear about landslides in Malaysia. Yeah, landslides, as you can see there, a long list of landslides occurring since 27. This is taken, by the way, from the Star, okay, dated 30th of December 2021. Again, as you can see there, the Star has listed down various cases of landslides occurring in Malaysia, and it's quite frequent, landslides that occurs in Malaysia. Again, why do landslides occur? Well, other than issues of engineering and all that aspect, we are talking about also heavy downpour, heavy rain occurring to Malaysia, again, due to the climate change. Now, I guess most of us do know about this, the Sustainable Development Goals, whereby Malaysia as a country has also signed this agreement in 2015 to implement this 17 sustainable goals. So, and from there, I just like to relate this issue to this point, where in 2016, the Malaysian government, together with the Construction Industry Development Board, or CIDB, launched this Construction Industry Transformation Plan, or Transformation Program, CITP. This was way back in 2016, and it is a 5-year program up to 2020. So this issue of the launching of the CITP was in evidence to the Malaysian government trying to improve the construction industry towards having more sustainable issues. So there are 3 elements that has been focused here. First is that the construction industry must be sensitive towards environmental sustainability. And number two is that in line with the requirements of green construction, meaning that the construction must be in line with green, and it must be also reducing carbon emission, CO2. And number three is that it must fulfill the requirements for carbon footprint. So this is the program that was launched in 2016 about environmental sustainability. Okay. Now, because of this exercise, that made me apply for this grant, whereby I was looking at various issues in Malaysia, especially in terms of construction industry, how we can assist the construction industry in Malaysia towards having a better system, a better material that we can have in Malaysia. As you can see, I've highlighted a few issues that has been pondering Malaysia, in terms of low quality of construction, and then you can also have some abandoned projects occurring in Malaysia, and there are also high demands. Okay, there are so high demands of quality housing by our citizens in Malaysia. Now, other than that, I've also raised here, I've given some 3 points about the waste that's available in Malaysia. As you can see here, these are waste from the agricultural sector. And then we have the issues about the depletion of earth resources, and also the CO2 emission from the cement manufacturing companies. So all this has affected the climate change, and this may have some influence on the climate situation in Malaysia alone. Now, this is a bit of literature review. Okay, so we are going to focus on the green, on the concrete. My study is focusing on the concrete. So what I'm going to explain here is that concrete is basically a material which consists of essentially 4 materials, which is cement, sand, aggregate, and water. So this is quite normal, quite well known to all of us. And of course, cement is one of the biggest contributor to CO2. Okay, globally. Okay, not in Malaysia, but globally. As you can see from my writing here, about maybe 5 to 7% of global CO2 emissions comes from the cement production. Okay, so that's how serious the situation is. Okay, the more we use cement, the more we are going to contribute towards the emission of CO2 to the atmosphere. And again, the cost aggregate, now this is in relation to the natural resource, the depletion of the natural resources. So the more we use the more we use concrete, the more materials that we require. Even cement requires raw materials from the earth, and the cost aggregate, of course, it comes from the Mother Earth. And then, as you can see again from this writing, for concrete alone, you need about 30 to 50% of volume of cost aggregate. Okay, to produce a concrete, you need about 30 to 50%. So that's a huge amount of huge amount of aggregates in a concrete. Now, other than that, as you can see here, the production of the aggregates also contributes towards the emission of CO2. Excuse me. Now, coming to green concrete, the area that I want to do for the research. So what I will be focusing on is trying to implement or integrate 4 types of waste materials that is available in Malaysia. Okay, so the first is the palm oil fuel ash. Second is rice-husk ash. Third is the palm oil fibre. Okay, and the fourth waste material is the recycled concrete aggregate. Okay, so these are basically what we call green concrete, as you can see from the writing just on top here. Okay, as you can see there, green concrete is defined as a concrete which uses waste material. Okay, or at least one of its components. This is the definition about green concrete. When we integrate waste material into concrete, so basically it is defined as a green concrete. So that is just one waste material. But in my research here, I'm trying to use basically more than one, which is four waste materials. into this concrete. So it's basically a mixture of 4-in-1. Now, talking about palm oil tree, okay, as you can see from this diagram, I'm sure all of us know what is a palm oil tree, and from here you can see that we can have our fruit bunch, your palm oil trunk, and then this is your trunk, okay, of the leaves. Now all this will contribute towards having this particular biomass. These are all the biomass produced by the palm oil tree. So you have your palm kernel cake, you have your palm kernel shell, you have your empty fruit bunch, and you have your mesocalc fiber. So from all these materials, these are all waste materials that can be used for various ways. And for my research, I will be using the fiber, okay, as I mentioned, and also the palm oil fuel ash and the palm oil the palm oil fuel ash and the palm oil fiber. Okay, so as you can see from this description, there's a lot of waste that has been produced from the palm oil industry. If I just remove this one to one side, okay, it's written there 100 million tons of biomass produced every year from the palm oil industry in Malaysia alone. Yeah. So there's a lot of waste that is being wasted, and sometimes it's being burned. So all this waste material needs to be utilized somehow. So therefore, of course, concrete is one of the ways that we can use to utilize all this waste material. Okay, so this is the palm oil fuel ash and palm oil fiber produced from the palm oil industry. So as you can see, the palm oil fuel ash comes from the burning of the palm oil shells. Okay, they are being burned in the palm oil industry in their boiler, and these are the residues produced by the boiler. And this is basically the palm oil fuel ash that is available, quite easily available in all palm oil industry in Malaysia. And this is the palm oil fiber, the type of palm oil fiber that I will be using also. So this is again available. This is again obtained from the palm oil fruits. Okay, when you squeeze them, when they squeeze the oil from these fruits, you are left off with this basically fibrous material, and they have been dried, and and usually they have been thrown away, or they are being used as part of the burner for the palm oil industry. So all these are waste material, okay, the palm oil fiber and the palm oil fuel ash. And other than that, I will be using rice-husk ash in the concrete. So rice-husk ash is essentially comes from the rice husk from the rice industry. Okay, so this is the husk that you burn. And again, all these materials are available easily in the open. Okay, so from my research, I obtain all these materials, either the palm oil fuel ash, the palm oil fiber, and the rice-husk ash from their respective industry. Okay, I just pay a few amount of money, and then we can easily get them and bring them back to our laboratory. So all these are very easily accessible for our research. So as you can see, both materials, rice-husk ash and also the palm oil fuel ash, as you can see there closely, they are very darkish in color. And but if you don't mind me saying, the palm oil fuel ash is more refined as compared to the rice-husk ash. As you can see there, it's a bit more coarser in shape. Okay. Now, these are some past research work done by various researchers on adding on using palm oil fuel ash as cement replacement. Okay, so I've combined all of this make them in one table, And as you can see from this table, and from you can see from this table, okay, most of the researchers have conducted work between 10% to 30% of palm oil fuel ash as cement replacement. Okay, and the results, as you can see, when they add 10% or 30% of palm oil fuel ash in as cement replacement, the results are quite reasonable as compared to the concrete with zero POFA. Okay, for example, in this case, Muhammad et al. 2014, at 0% POFA, they get a value of 137. At 10%, they got a value of 152, which is much better. At 20%, they get 153, which is even higher. And at 30% of cement replacement, the value reaches up to 146. So it seems to be quite reasonable. The same goes to Islam et al. 2016. They've done also a reasonably good research work in terms of palm oil fuel ash as cement replacement, and the results are quite reasonable. Now, other than that, we can also see that researchers have gone beyond 30% of cement replacement. They have gone up to 50%, 60, 70, and even 80% of cement replacement of POFA. And the results are quite okay. Okay, as you can see from Al-Subari, the first one in 2016, he reaches a value of about 69 up to 65 megapascal as compared to 67 with zero POFA. So it's quite okay. But for Awal and Shihu, 2015, the results are not favorable. As you can see there, it's quite low as compared to 0% POFA at 44.4%. So this is quite inconsistent in terms of the results. And again, in 2013, the same researcher, Awal and Shibu, they did the same research. Again, the results are quite low as compared to 0% POFA. So in that sense, we can see that from this literature review, percentage between 10% to 30% of palm oil fuel ash as cement replacement is the most acceptable in terms of getting a good concrete strength. Now, in terms of past research on rice-husk ash as cement replacement, again, as you can see, I've listed down a few researchers, and they've done also various percentages of cement replacement with rice-husk ash, as you can see there, from 10% up to 50%. And again, the same approach applies. I was looking for some of the nearest results that we can observe from their past research, and as we can see, a percentage of between 10 to 20% seems to give the most acceptable percentage of concrete strength when you replace cement with rice-husk ash. Excuse me. Now, in terms of the RCA is the recycled concrete aggregates. I will explain it what I mean by recycled concrete aggregates. So in this research, again, I compile various researchers, past research on research work conducted on replacing coarse aggregates with recycled concrete aggregate. Again, as you can see there, researchers have tried to replace coarse aggregate from 10% up to even to 100%. But again, from our observation and compilation, we can see that when we change an amount of about 30%, we will get a good strength in terms of concrete. In terms of concrete strength, we seem to get a reasonably good result when we only replace 30% of recycled concrete aggregate. All right, so as you can see there, so that's how I decided on the type of percentages that I will be using for my green concrete. Now, as you can see there, 50% is also was observed to be quite okay in terms of the results. But then I have decided that based on this, we have selected 30% as the maximum amount of RCA that we will be using in this green concrete. Now, going on from there, this is the framework of how we will determine the green concrete mix. Okay, this is the framework. All right. So what we are going to do is, the challenge is in this research is to use as little, the first one is to use as little cement as possible, use as little cement and aggregate as possible. So this is what we are trying to do. But of course, based on our literature review, we have a limitation to how much that we can replace cement and how much that we can replace our aggregates. And then from the literature, also we can see that there are no evidence on the hybrid combination of these three materials: the palm oil fuel ash, the rice-husk ash, and the recycled concrete aggregate in a single concrete mix. So there's no study that has ever been done on using all these three materials, all these three waste materials. And then from here, what we're going to do is we are going to do an extensive study on trying to obtain the optimum results that we can use to have a certain amount of strength for this green concrete. So with that respect, what we have done is we have done the research in 4 stages. Okay, we have stage 1, stage 2, stage 3, and stage 4. Okay, so stage 1 and stage 2 is essentially on the cement replacement. We are focusing on only replacing cement. No other waste materials are being added. So for first stage, my focus is on obtaining an optimum percentage of palm oil fuel ash in our concrete mix. All right. So the percentage that I will be using, just let me remove this to one side. So the percentage that we will be using for the palm oil fuel ash is between 10%, 15, 20, 25, and 30% of palm oil fuel ash replacement with cement. Yeah. And then for stage 2, I will only be focusing on rice-husk ash as cement replacement. No other waste material will be used in this study. And in this study also, I will be using replacement percentage between 10% up to 30%, as you can see on the screen now. So once I've completed stage 1, I will obtain the optimum percentage of POFA. And once I've completed stage 2, I will achieve the optimum percentage for rice-husk ash. And from there, I will do a combination in stage 3. I will do a combination between the optimum palm oil fuel ash and the optimum rice-husk ash. Now in this study, I will explain later, I will show you later what are the percentages that is acceptable to obtain a certain amount of strength that we have set for this green concrete. Now, after achieving this mix of optimum percentages of this waste material, okay, I will go to stage 4, where in this stage I will combine all three waste material, the optimum POFA and RHA plus a percentage of aggregate replacement. So again, the percentage of aggregate replacement I will be using is about 10% up to 50% replacement of RCA in this green concrete. So these are basically the stages that I will be used to obtain the optimum mix for my green concrete. And finally, which I do not show here, which is stage 5, is adding the palm oil fiber. Okay, so that's a different stage. So I will discuss right now all these 4 stages one by one to all of you. Okay, materials. Now before that, we will look at the materials preparation. So you need to know how the materials are being prepared. So as you can see there, these are the equipments that we need for our materials preparation for palm oil fuel ash and also for the rice-husk ash. And as you can see there, both palm oil fuel ash and the rice-husk ash will be dried oven, okay, for 24 hours, and then they will be sieved using this 300 micron sieve analysis equipment, and then from there, okay, we will put them in the grinder using the Los Angeles abrasion machine, and the machine will grind them so that we will achieve a very fine raw material of POFA and rice-husk ash within the size of 150 microns. Okay, so that's our target. Okay, to get the size as fine as possible, and we managed to get this for both materials. Both are as near as possible to 150 microns. All right. So this is the first level of the material preparation in terms of the palm oil fuel ash and the rice-husk ash, where we try to get the size of the material for POFA and rice-husk ash at about approximately 150 microns. Now, this is the recycled concrete aggregate that I was mentioning to you about just now. So what we have is we have all these concrete cubes left over in our laboratory, and we so happen to have a concrete crusher in our lab, and this concrete crusher will crush these cubes and make them into small pebbles. Okay, and what we did was we are looking for a size between 5 to 10 millimeter of RCA. We are going to use that size, and of course we have to use a sieve to make sure that we obtain the size that we are looking for in terms of the recycled concrete aggregate. Okay, so it's a lot of work. The process takes a bit of time. Okay, I'll just show you again. Okay, to get this palm oil fuel ash, the rice-husk ash, we have to dry them, grind them, sieve them. Okay, and then we have to make sure that we have enough amount of materials for our mix. The same goes to the recycled concrete aggregate, where we have to grind them. We have to crush them, sieve them, and make sure that we get the right sizes that we are looking for. Okay, so the material properties. All right, so in terms of the palm oil fuel ash and rice-husk ash, we have to do a chemical composition test to make sure that they have sufficient chemical properties to act as a cement replacement, or what we call as a pozzolanic material. So this is the machine that we use, the X-ray fluorescent test machine, XRF, was used to determine the chemical properties of both palm oil fuel ash and rice-husk ash. And these are the results that we managed to obtain. Okay, as you can see from the table, we did the chemical composition for Portland cement, for palm oil fuel ash, and also for rice-husk ash. So we have 3 results, and these are the distribution of the chemical compound, okay, in the material. All right, so as you can see there, okay, the first four materials there, silica dioxide, aluminum dioxide, iron oxide, and calcium oxide, are basically the 4 top materials that you need in the cement. Okay, especially silica dioxide and calcium oxide. These 2 materials, silica dioxide and calcium oxide, are the 2 key materials in the cement. And as you can see from this chemical composition, both POFA and rice-husk ash has a very large amount of silica dioxide, okay, 51% and 74%, respectively. But unfortunately for the calcium oxide, both POFA and rice-husk ash both have very little amount of calcium oxide as compared to the Portland cement, the ordinary Portland cement. As you can see there, about 22% of silica dioxide, okay, much less than POFA and RHA, but a whopping amount of 62% as compared to POFA and RHA for calcium oxide. So, but essentially, all these 2 materials are the main actors in the cement, where when you add water, okay, H2O to these materials. They will combine, they will react and form into a gel. Okay, so as you can see there, by adding POFA and RHA, okay, you have extra silica dioxide, which will react with the calcium oxide, and this is where the extra, well, we suspect that this is where the extra strength of the green concrete comes in. Okay, when you have that extra silica dioxide comes into play with the calcium oxide. Now, from this test also, as you can see, POFA, based on the ASTM C618 category, POFA is classified as a Class C pozzolan, whereas the rice-husk ash is classified as Class F pozzolan. Okay, now this is one test that we did from our mix. So I haven't shown you the green concrete mix yet, but this is the green concrete and the ordinary concrete that we did to see how green concrete sets as compared to ordinary Poland cement. So as you can see from this test, this is a simple test. This is the apparatus, what you call the VCAT apparatus. This is available in all concrete laboratory. If you don't have it, then it's a worry. But everybody should have this VCAT apparatus, and which is a basic material, basic apparatus for testing concrete materials. So as you can see from this result, using our waste material of OPC, POFA, and RHA, the setting time is a bit longer as compared to the ordinary Poland cement. Okay, ordinary Poland cement takes 120 minutes initially before it finally sets at 180 minutes. As compared to the green concrete, it takes 150 initial setting, and by 210 minutes, only then it will have its final setting. Okay, based on the testing apparatus and its guidelines that we follow. So as you can see there, green concrete is, as you can see, basically will take longer time to set as compared to the ordinary cement. So this is one thing that we have found out from our study. Now, other than that, we did a series of further testing on the materials for palm oil fuel ash, for the rice-husk ash, and also for the palm oil fiber. Okay, we did electron microscopic study, or the SEM. Scanning electron microscopy was conducted to analyze the morphology of the waste material, namely POFA, RHA, and POF. So this is the equipment that was used. Now this work was conducted at the materials laboratory at the Jabatan Kerja Raya JKR Kriet, which is located in Malacca. Yeah. All right. This is not UTHM or not, but this is available in JKR. So we did a study by using their machine, and this is what we obtained. The morphology for POFA and RHA, as you can see there, from these two pictures, POFA shows a bit more flaky and bit more irregular size distribution, and a bit more chunkier in terms of size. And then, unlike the rice-husk ash, the particles are more well distributed. Okay, even though they are irregular, but they are well distributed as compared to palm oil fuel ash, which is more irregular, more less. You have various sizes as well, and then it's a bit more flaky, a bit more thinner as compared to this rice-husk ash material. Okay, so it's the two different characteristics in terms of morphology. One with various, the rice-husk ash shows better distribution. POFA shows it's a bit more irregular in terms of size, also in terms of its distribution, which is, to me, is very good also, because at the end of the day they will combine and will become into one material. Now this is the morphology for the palm oil fiber that we will be using. So as you can see, this fiber shows a very good fibrous. The trend of the fiber shows good lengthy fibers there, as you can see in this picture. Okay, they are rough and porous, displaying. Okay, it's also porous, by the way, it displays parallel streaks along the length of the fiber. So this is the typical fiber that we'll be using in our concrete. And this is the aggregates and the RCA that we will be using in our mix. The one on the right hand side is the normal aggregates, whereas on the one on the right hand side, this is the recycled concrete aggregates that we produce in the lab. Okay, and the sand that we use in the mix, okay, is sand, river sand, passing 5 millimeters. The size of the material is roughly about 5 millimeters. Now the concrete mix design, this is based on the American Concrete Institute, ACI, and the target of the concrete strength is about 30 megapascal at 28 days. So this is our target strength at 30 megapascal at 28 days. The water cement ratio selected was 0.57. Now this is the mix of the concrete. Okay, as you can see there, the distribution is that cement is about 400 kilogram per meter cube. Coarse aggregate at 756 kilogram per meter cube. Fine aggregate, which is sand, in other words, is 951 kilogram per meter cube, and water you require 228 kilograms of water in a 1 meter cube of concrete mix. Now this is the normal concrete mix. It has no waste material as yet. Okay, so we now can come to the experimental results. Right, so what I did now is I've replaced now this is the stage 1. As I mentioned, we have 4 stages, stage 1, 2, 3, and 4. This is the first stage where we replace cement with palm oil fuel ash, okay, partial replacement, between 10% up to 30% of cement replacement with palm oil fuel ash. And of course, at 0%, that means this is totally using cement with no POFA. So from the results, as you can see, we did all this, and you can see that POFA between 10% to 20% shows a reading of 30, 31.6, and 32.4 megapascal. Okay, so with this 3 replacement percentages, it shows a reasonably good result of concrete strength in compression, by the way. So as you can see there, the arrow shows the target strength, which is 30 megapascal. So this is palm oil fuel ash as a replacement for cement, and we managed to obtain this sort of result between 10% and 20% of palm oil fuel ash shows a reasonably good result. Okay. Now what about the rice-husk ash? Now this is the second stage of the work. Now as you can see there, again the same percentages, from 10% up to 30% of rice-husk ash was used to replace cement. Okay, and as you can see, again the same trend was observed between 10% to 20% of rice-husk ash as cement replacement. The results of the concrete strength shows higher than 30 megapascal. Okay, anything below 30, we will ignore them. Okay, as you can see also at 0%, the strength of the concrete is at 36.7. So again, you can see how much strength the green concrete has able to be achieved within their respective mix. Now this is the stage 3 of the study, where now we are combining the optimum POFA and the optimum RHA as replacement. So with that, what we did was we combined various percentages of palm oil fuel ash and rice-husk ash in the mix. So for example, we have a 10% POFA and 10% rice-husk ash in this mix, and then it goes on right to the end where we have palm oil and rice-husk ash at 20% each. So basically, you're talking about 40% of waste material in this particular concrete mix design. Right, so 10, 10, 10, 15, 10-20, 15-10, 15-15, and so on. So these are the distribution of the percentages of the POFA and RHA in this concrete mix. So from again, the target means the target strength of the concrete is still at 30 megapascal. And what we can observe with this combination of POFA and RHA, okay, we can see that with 10% of palm oil fuel ash and 15% of rice-husk ash, we have managed to obtain a value higher than 30 megapascal. Okay, as you can see from 10% POFA and 10% rice-husk ash, we also managed to get 34.7, but we selected this one because we have higher amount of waste material in this concrete mix, which is 10% and 15%. So that's about 25% of waste material in this concrete mix. And yet we still managed to get higher than the target concrete strength of 30 megapascal. All right, so 25% of pozzolanic replacement was achieved for this particular study. Okay, now we proceed to the stage 4, where we are going to we have found out the optimum combination of POFA and RHA, which is 10 and 15% respectively. And now we want to add RCA replacement in the study. This is the stage 4 study. So we are going to add RCA from, as you can see from this table, the C is the RCA, 10%, 20%, 30, 40, and 50% of RCA replacement in this concrete mix. And the POFA and the rice-husk ash maintain at 10 and 15%. Okay, 10, 15, 10, 15. Okay. So again, our target strength of concrete is 30 megapascal. And then again, from this study, at 28 days, a mix of 10 POFA, 15 rice-husk ash, and 20 coarse aggregate, 20 recycled coarse aggregate, we achieve 32.8 megapascal. So from this particular mix, as you can see, we have 25% pozzolanic, 20% RCA. So we are talking about nearly 45% of waste replacement in this particular concrete mix. And yet, with this 45% of waste replacement, we can still achieve a concrete strength of 32.8, higher than 30 megapascal, which is our target strength. So that's stage 4, which we have achieved. So this is practically the percentage of waste material that we'll be using in our green concrete. 10% POFA, 15% rice-husk ash, and 20% recycled concrete aggregate. All right. Okay, so the green concrete, to achieve a compressive strength of 30 megapascal only, all right, so you must be aware that this study is only on focusing a strength of 30 megapascal. So the POFA is at 10%, the rice-husk ash is at 15%, and the recycled concrete aggregate at 20%. Okay, now I want to further discuss the results of the green concrete when we add palm oil fiber or POF. All right. So in this study, the palm oil fiber, okay, we obtain again from the factory, from the palm oil industry, and we cut the length of the fiber up to 2 centimeters in length. Okay, up to 2 centimeters in length, and they are also soaked in water to avoid them to be too dry. We soak them in water. And the study also is investigated by adding palm oil fiber at 0.25%, 0.5%, and 0.75% by weight of cement. Okay, so this is the study that this is the percentage that we will be using based on our past past literature review. This is the common percentage that's being used by most researchers in adding palm oil fiber in the cement. Okay, so this is the results that we managed to do. We did various types of results for concrete. All right, so I may be running out of time. Okay, so I just proceed. Hang on. I think I still have a bit more time, about 10 more minutes. So this is the results that we did. The first is the workability study of the green concrete mix with various percentages of palm oil fiber. Okay, as you can see there, GC1 at 0.25%, GC2 at 0.5%, and GC3 at 0.75% of palm oil fiber. So as you can see there, at 0% of palm oil fiber, this is zero. This is the green concrete, but with 0% palm oil fiber, we achieve 90 millimeters of workability. But when we add the fibers at the various percentages, the workability drop down to 65 up to 50 millimeters. Okay, it gets more stiffer as we add more fiber in this concrete mix. Now this is the density of the green concrete with the palm oil fiber. So again, we did this study on the density of the green concrete with palm oil fiber. So as you can see, the density of the concrete does not change that much. Okay, very unfortunately, it doesn't change that much. At 0% palm oil, the green concrete at 0 fiber is 2250. Whereas with 0.25% fiber, you have 2315. It adds up a bit more in terms of density. So then as you have more fiber, the result shows a bit slightly lower density than the 0% palm oil fiber of the green concrete. But then again, in saying that, the results are almost quite similar in terms of density. So roughly about, I could say, nearly 2,300 kilogram per meter cube of green concrete density was achieved in this study. This is the compressive strength of the green concrete mixture with palm oil fiber. Okay, so as you can see, the results are tremendous. All of them achieve more than 30 megapascal, but the best result shows at 0.25% palm oil fiber. The result shows a whopping value of 40.4 megapascal, very much a 10 megapascal increase from the target strength of 30 megapascal. Okay, but even at 0.75% of palm oil fiber, the green concrete shows good results of 30 megapascal. All right. So all in all, the result shows good in terms of its performance in compressive strength. Now, this is the study of the compressive strength that we did, and we monitor the strength up to 180 days. Okay, as you can see from the title, it is up to 180 days. So the strength shows again remarkable values. Now the red line here is the green concrete with 0 fibers. Okay, the green concrete with 0 fibers. Whereas the one with the green is the green concrete with 0.25% fiber. So as you can see, the strength is not only better than the green concrete with 0 fiber, but the strength seems to be showing an increment up to 180 days. It is not showing any dropping in strength. It is showing an increment. The same goes to the other mix as well. Okay, both are showing an increment as compared to the 0% of fiber. All right, so this shows that the concrete strength is increasing as the days goes by. Okay, so it has gone more than 28 days, and it shows that the strength is still increasing. Okay, water absorption. Again, this is another test that we did for the green concrete mix. So the one with the highest amount of palm oil fiber shows the highest amount of water absorption. So this is not a good indicator. Whereas the least amount of palm oil fiber shows the least amount of water absorption to the green concrete. So this seems to be something which is acceptable, which is very near to 0% of fiber, 6.07 and 5.98 of water absorption. And this is the water absorption of green concrete up to 180 days. Again, as you can see, the tendency for the material to absorb water is still there, but it seems to be reducing as the number of days increases. So as you can see, by 180 days, you have less amount of water absorption to your material for all types of mix. Now, this is the split tensile strength of green concrete. Okay, so the strength shows above the green concrete with zero fiber. So of course, when you add fiber, you are going to increase the tensile strength of the concrete. So again, at 0.25%, the strength is about 2.58 as compared to 2.3. And also for 0.5%, the strength seems to be higher at 2.74 as compared to the other results. Okay, so as you can see, all in all, when we add fiber, obviously we are going to increase the tensile strength of the concrete mix. Now again, this is the strength of the tensile strength of the green concrete up to 180 days. Again, the strength shows an increment of its value. Okay, so as you can see there, all of them shows an incremental tensile strength increment from 28 days up to 180 days. So this shows that the strength is always improving with time. Now again, this is the last test that we did. This is the thermal conductivity test, and this test was conducted at the University of Malaya, and they have this equipment to measure the thermal conductivity. And this is the equipment and the specimen that we did with all the thermal couplers and the data logger, all provided by University of Malaya. And this is the result that we managed to obtain from the thermal conductivity of green concrete with palm oil fiber. So as you can see there, okay, the normal concrete for the K value, K is the thermal conductivity value for the material. For normal concrete is about 1.6 to 2.25. And the one that we obtained for the green concrete is much less than that, which is about, the most is about 1.49, okay? Which is still less than 1.6. So this shows that the green concrete is a good conductor for heat. So again, finally, this is the last slide, the overall conclusion on the green concrete mix. So from the green concrete mix, by adding palm oil fuel ash, rice-husk ash, recycled concrete aggregate, and palm oil fiber, it has the potential to replace the conventional concrete mix, okay, because firstly, it has achieved the compressive strength beyond 30 megapascal. Okay, secondly, it shows better performance in its mechanical and thermal properties compared to conventional concrete. And finally, what I can recommend is that green concrete is fully recommended for any future construction in the Malaysian context. So with that, I end my talk today. So these are some of the acknowledgement, the fundamental research grant from the Ministry of Higher Education, my students who did this research. These are some of the copyrights that I obtained from this research, book chapters, publications that was published through the years. And we come to the Q&A if we have time. So I leave it to the moderator to decide whether we have time or not for any Q&A. Thank you very much.
Okay, thank you very much, Prof. This is a great sharing session, great knowledge for green concrete technology. Okay, so before we go end of this session, okay, Prof, we have one question from the audience actually. Okay. So the question is there the green concrete already implemented in building?
Oh, is there any being implemented?
Yeah. Is there the green concrete
Yes.
green concrete already implemented in
Yes.
building?
Yes, I understand. Yes, technically, my answer is yes. It has been done because now cement is incorporating other kinds of waste material, especially from the waste from the coal bottom ash, or they use fly ash from other not necessarily from agricultural materials, but from other types of materials. Okay, so they have been using, and it is available in the market where cement and fly ash is added together in the cement bag. Okay, so
Okay.
it has been implemented, but
Okay.
for my study using agricultural waste, it has yet to
Mhm.
be fully implemented in the construction
Full.
industry.
Okay, this is a great one for the green concrete technology actually. So what is the percentage of the age they are used for the implemented the green concrete actually during
Uh,
their develop the concrete?
well, when
What
they
is the
use
percentage?
the
What is the
percentage of the waste
percentage?
material, is it?
Yes, yes, yes.
I would
The
say,
ash
I
material
think,
they use.
yeah, from my study, you cannot go more than 30%, or at least
Oh,
as I showed from my study, I can go up to
okay.
45% of waste material in my concrete because I've
Okay.
used three different types of material plus fiber. So altogether, it's
Okay.
about 45% of waste
Mhm.
material in my concrete. So you can go up to 45%, and you can still manage
Okay.
to get good concrete strength beyond the target strength of 30 megapascal. So,
Okay.
but to be safe, it is better up to, as I can see from most study, mostly it's about 30% of waste material in the concrete.
Oh,
Okay. But from my
okay.
study, from my material that I use, I can go up to 45%.
45%.
Yeah.
Right. Okay, bro. I think this is not more comment on the chat box, on comment box here. Okay.
Yeah.
Now we can end off this session. All right. So thank you very much, Prof, for your spending time. All right. For your great knowledge on the green concrete technology. Okay. Hopefully, this sharing session and knowledge regarding green concrete technology beneficial for our student and our researcher, okay, from the outsider and so on, okay, and can initiate the idea to improve the green concrete technology for industry and so on. Okay, Prof. Thank you very much.
Thank you.
Thank you for audience watching for this live webinar. All right. See you next webinar. Okay. Bye
Thank you. Thank you
bye.
very much.